So with delta H, when you're calculating using heats of formations, so a heat of formation means the amount of heat absorbed or released when forming that particular element or compound. And so from the video involving heats of formation, you should have remembered that the heat of formation, so delta H of F equals 0 for elements in their natural state. So if it's an element in their natural state, it has a heat of formation of 0. So what that means is, for example, fluorine gas, F2 gas, would have a heat of formation equal to 0. And that's because, again, heats of formations are derived from elements in their natural state. So for example, the heat of formation of CO2 gas is derived from this equation. Now with heats of formation, and this is actually carbon graphite, that's actually the natural state of carbon. For heats of formation, the amount of product has to be 1 mole. So this is called a formation reaction. So a formation reaction is you have elements in their standard states produce 1 mole of product. And so here graphite is the natural form of carbon, oxygen gas is its natural form, and we produce 1 mole of product. This is referred to as a heat of formation reaction. So again, it's elements in their standard states have a heat of formation of 0. So therefore, when you measure the heat absorbed or released in this reaction, it comes strictly from the formation of the product, because the reactants have a heat of formation of 0. So whatever is measured in this reaction is the heat of formation of CO2. And that's how they determine the heats of formation is they start from the elements. They determine how much heat is absorbed or released from the reaction for 1 mole of product. And so this is what they call a heat of formation reaction. So here, for example, O2 liquid. Well, O2 liquid is not the natural state of O2, so it would not have a heat of formation of 0. So if you were to actually write the formation equation, it would be O2 gas to O2 liquid. So however much heat's released when O2 gas goes to O2 liquid, that would be the heat of formation of O2 liquid. Now bromine liquid, Br2 liquid, it does have a heat of formation of 0 because bromine's natural state is a liquid. So that one would have a heat of formation of 0. H2O gas, it's a compound. Its heat of formation would not be 0. It would look something like this. So H2 gas plus 1/2 O2 gas, H2O gas. So that one would have a non-zero heat of formation. And by the way, the different physical states have different heats of formation. So H2O gas is different than H2O liquid. Now sodium solid, sodium is naturally a solid, so its heat of formation would be 0. C6H12O6, it's a compound. So compounds, their heat of formation is not 0. So if we were to write the formation equation for this, it would look something like this. So again, heat of formation equations have to be elements in their standard form, give you the product. So here this would be 6, 6, and 3. So you just know that metals, their natural state is solid. The only metal that's natural state is not a solid is mercury, which is a liquid. And for non-metals, you know, if you remember the acronym Brinkelhoff, those exist as diatomic elements, which exist as gases except bromine and iodine. So bromine is naturally a liquid, iodine is naturally occurring as a solid. Of course, the noble gases are noble gases, so they naturally exist as a gas. And so this would be the formation equation of C6H12O6. So again, it's derived from elements in their natural state to give you 1 mole of product. So again, the key thing is that you have 1 mole of product in the reaction. That's a formation equation. Now we go to N2 gas. Nitrogen exists naturally as a gas, so it would have a heat of formation of 0. And then we have H gas. Well, H gas is not the natural form of hydrogen. Hydrogen is diatomic, so it would be H2. So again, to look at this formation equation of H gas, it would be 1/2 H2 gas gives H gas. And so there would be some heat of formation associated with this reaction. So again, heats of formations that come from elements in their natural state are 0. Heats of formations of compounds are always non-zero. The heat of formation equation has elements in their standard states as reactants, and you produce 1 mole of product. So with heats of formations, we can use it to solve for delta H of reaction, or we can use it to find heats of formations of other compounds or elements. And so heats of formation is a different route than Hess's law. So you can use either one to determine the heat of reaction. So here we have this reaction involving copper 1 oxide plus oxygen gives us copper 2 oxide. It tells us the heat of reaction for this synthesis reaction. It gives us the heat of formation of copper 1 oxide and says what's the heat of formation of copper 2 oxide. Now with heats of formations, it's always the heat of formation of products minus the sum of the heat of formation of reactants. So remember, products is final state, reactants are initial state. And so what we're going to do is 2 times the delta H of reaction equals 2 times the heat of formation of copper 2 oxide minus the heat of formation of copper 1 oxide. Well, copper 1 oxide we have, and we have the heat of reaction, so we can solve for the heat of formation of copper 2 oxide. So again, one of the most common mistakes that I've seen made in these types of problems is remember a negative and a negative make a positive. So this minus negative 168.6 becomes a positive or plus 168.6. And now you move everything over to get like terms on the same side. We get 2 times the heat of formation of copper 2 oxide equals negative 314.6. And so the heat of formation of copper 2 oxide is negative 157.3. By the way, when the heat of formation is exothermic, that means that the product is more stable than the reactant. So when we make copper 2 oxide from its elements, it's going to be a more stable substance than the elements itself. Here we have another problem. We have the combustion or the burning of acetylene in the air given the following combustion reaction. Now sometimes, don't be surprised if in thermochemical equations you may see a fraction, and the reason they do this, for example, the reason they use 5/2 O2 is so that there's 1 mole of acetylene. And typically in thermochemical equations, one of the reactants or products is set to a coefficient of 1, so that for every 1 mole of acetylene, we produce this much heat. And so that's why you see a fraction in front of O2. So to make acetylene a coefficient of 1. And it gives us the heat of formations of CO2, H2O gas, and ask what's the heat of formation of C2H2. So again, delta H of reaction equals the heat of formation of products minus the sum of the heat of formation of reactants. And you need to know this equation here when calculating heat of reaction. So again, it's going to be 2 times the heat of formation of CO2 plus the heat of formation of H2O minus the heat of formation of C2H2 plus 5/2 heat of formation of O2. So when we work this out, the good news is that the heat of formation of O2 gas is 0, so that just drops out, and we get this expression. So now what we want to do is we want to move heat of formation over to the left and move this negative 1255.8 over to the right, and we get the heat of formation of acetylene is 227 kilojoules per mole. And this is for acetylene gas. Now, if you had acetylene liquid, for example, it would have a different heat of formation. So in this problem, we're looking at the conversion of ammonia to nitric oxide, and it's a combustion reaction. So we have ammonia plus O2 gives us NO and H2O gas. Calculate the delta H of reaction. It gives us the heat of formation of ammonia, nitric oxide, and H2O gas. And so from this, we need to calculate the delta H of reaction. So again, you're not expected to know the heats of formation of the reactants and products. Those will be provided. If you're doing your homework, you may have to look these up in a table. Make sure you picked the table in the back of the textbook has 3 columns. The first column is heats of formation. So make sure you use the correct column in the back of the book if you have to look up these values. So again, heat of reaction equals the sum of the heat of formation of products minus the sum of the heat of formation of reactants. So we have to multiply the heats of formations by the coefficients in the balanced chemical equation. And this is a common mistake that's been made, is people forget to multiply the heat of formation by the coefficient, and of course that results in an incorrect answer. So now we just multiply the coefficient by the heat of formation. We get this expression here, and we see that the delta H of reaction is a negative 906 kilojoules per mole. And so again, combustion reactions are exothermic. And in the last problem, this is actually a combination of delta H of reaction and thermochemical stoichiometry. So we have hexane combusts with oxygen to produce CO2 and steam. If 550 grams of steam are produced, how much heat is released from the reaction? And it gives you the heats of formations of the reactants and products. So remember, what we're going to have to find first is the delta H of reaction of the balanced chemical equation, because once we know the delta H of reaction, we can find out how much heat is released by the production of 550 grams of H2O. So the balanced chemical equation looks something like this. So now that we have the balanced chemical equation, we can calculate delta H of reaction. So again, make sure you multiply the heats of formations by their coefficients, and it's always products minus the reactants. So we work this out. We get a delta H of reaction of about negative 7,709.8 kilojoules per mole. So that's the delta H of reaction. Now that we know that, we can determine how much heat is released when we combust we produce 550 grams of steam. So remember, delta H of reaction equals the Q of reaction divided by, in this case, the moles of steam produced. So the heat of the reaction is equal to the delta H times the moles of steam. Well, the delta H we already have. The moles of water we can find. Now, depending on if you use 18 or 18.02, the moles will differ, but that's accounted for in the range of the answer. So as long as you're close to the answer that I get, that's fine. Usually like plus or minus 30 is the range we use. And so we know that 14 moles of H2O produce this much heat, and we get that from the balanced chemical equation. So 1 mole of H2O produces negative 550.7. So if 1 mole of H2O produces this, and we have 30.56 moles, well, then we can calculate how much heat is released. So it'd be about negative 16,830 kilojoules. And so in this problem, you didn't have to include the sign, so you could put 16,830. And again, remember the range for the acceptable answers, roughly plus or minus 30. So as long as you're in that ballpark, it would have been correct. And so again, this is a combination of thermochemical stoichiometry and heats of formation. So we first had to write the balanced chemical equation, determine the delta H of reaction. From that, we can know how much heat is produced by a certain number of moles of steam. We found out the moles of steam that we have. We find out how much heat is produced by 1 mole of steam. Then we can find out how much heat is released with 30.56 moles of steam.